What if everything we know, every star, every atom, every force shaping the cosmos, could be traced back to a single, elegant equation? Picture a theory so profound it unravels the deepest secrets of existence, bridging the gap between the quantum world and the vastness of space-time. This isn't just science fiction, it's the holy grail of physics, the theory of everything. For centuries, the brightest minds have chased this dream, from Einstein scribbling equations in his study to modern physicists colliding particles at near light speeds. Yet here we are, standing at the edge of a cosmic mystery, wondering, after all this time, have we finally cracked the code? Think about the sheer scale of what this theory promises. It wouldn't just explain how gravity works or why electrons behave the way they do. It would reveal the underlying harmony of the universe itself. Imagine holding a key that unlocks not just one door, but every door, from the birth of black holes to the flicker of a thought in your mind. But here's the twist: the closer we get, the more the universe seems to resist. For every breakthrough, like string theory or the discovery of the Higgs boson, there are new puzzles: dark matter, quantum entanglement, the unsettling fact that gravity still refuses to play nice with the other forces. It's as if the cosmos is teasing us, dangling answers just out of reach. So where does that leave us today? Some say we're on the brink of a revolution, with cutting-edge experiments and bold new ideas reshaping our understanding. Others argue that the theory of everything remains a beautiful mirage, always receding into the distance. In this video, we'll journey through the triumphs and setbacks of this epic quest, meeting the visionaries who have dared to dream big and confronting the questions that keep physicists awake at night. Whether you're a science enthusiast or just curious about the universe's grand design, one thing's certain: the search for the theory of everything isn't just about equations. It's about our unshakable human desire to make sense of the cosmos and our place within it. So let's dive in. The answers, or perhaps even better, the next set of questions, are waiting. To understand why the theory of everything feels so tantalizing yet just out of reach, let's rewind to the early 20th century, when physics split into two seemingly irreconcilable worlds. On one side, Einstein's general relativity painted gravity as the curvature of space-time, a smooth, cosmic stage where planets and stars danced. On the other, quantum mechanics revealed a chaotic subatomic realm where particles popped in and out of existence, governed by probabilities, not certainties. Both theories worked flawlessly in their own domains, but when scientists tried to merge them, the math exploded into nonsense. It's like trying to stitch together a symphony and a jazz improvisation, both beautiful, but their rules refuse to harmonize. Einstein spent the last 30 years of his life chasing this unification, scribbling equations in near isolation, convinced the universe wouldn't play by two separate rulebooks. He called it his unified field theory, but the tools of his era weren't enough. Fast forward to today, and we're still grappling with the same rift. Take black holes, for example. Relativity describes them as massive objects warping space-time, while quantum mechanics insists information can't just vanish inside them. When these theories collide at the edge of a black hole, physicists are left scratching their heads. Enter string theory, perhaps the most ambitious attempt to bridge the divide. Imagine if every particle in the universe weren't a dot but a tiny, vibrating string, different harmonies creating different particles. It's an elegant idea, but there's a catch. String theory requires at least 10 dimensions, and we've only ever seen 4. Then there's loop quantum gravity, which suggests space-time itself is woven from microscopic loops. Both theories are mathematically stunning, but neither has produced a testable prediction. It's as if we've invented two different languages to describe the universe, yet neither can translate the full story. So why does this quest matter beyond satisfying scientific curiosity? Because unification isn't just about tidying up equations, it's about rewriting our cosmic narrative. A true theory of everything could reveal how the universe began, whether parallel universes exist, or even why time flows in one direction. It might answer questions we haven't thought to ask yet, but here's the humbling truth. Every time we think we're close, the universe throws us a curveball. Dark energy, for instance, is accelerating the expansion of the cosmos, and we have no idea why. Maybe the real lesson is that the universe isn't just a puzzle to solve. It's a reminder that some mysteries keep us curious, driving us to look deeper. Einstein's quest for a unified theory wasn't just a scientific pursuit, it was an almost poetic obsession. By the 1920s, he had already reshaped our understanding of space, time, and gravity with relativity. Yet he couldn't shake the feeling that the universe's forces were pieces of a larger puzzle. Picture him in his Princeton study, chalkboard crammed with equations, chasing a single framework that could explain both the gentle pull of gravity and the crackling energy of electromagnetism. But the tools of his time were like trying to map the ocean with a teaspoon. Quantum mechanics was still in its infancy, and the strong and weak nuclear forces key players in any modern unification hadn't even been discovered yet. What's fascinating about Einstein's struggle isn't just the science, it's the human story. Here was a man who'd overturned physics twice before, yet spent decades hitting wall after wall. Colleagues quietly whispered he was wasting his genius, but Einstein pressed on, convinced elegance hid beneath the chaos. His notebooks from this period reveal pages of crossed-out calculations, dead ends, and moments of frustration. In one letter, he admitted the math felt like a bird chirping outside a locked window, close enough to hear but impossible to grasp. Yet his so-called failures planted seeds for future breakthroughs. Einstein's insistence that gravity and electromagnetism must unite forced physicists to think bigger. When later scientists discovered the nuclear forces, they didn't abandon his dream, they expanded it. Today's theories, like string theory or loop quantum gravity, owe a debt to his stubborn vision. They're grappling with the same core question: how do we reconcile the cosmic and the quantum? There's a lesson here that transcends equations. Einstein's unfinished work reminds us that science isn't just about answers, it's about asking the right questions. His hunches about hidden unity inspired generations to look deeper, even when the path wasn't clear. And perhaps that's the real legacy of his quest. Not a single theory, but the courage to keep searching when the universe refuses to give up its secrets easily. If the universe were a grand symphony, the standard model would be its sheet music, an astonishingly precise guide to the dance of subatomic particles. Since its development in the 1970s, this framework has predicted the behavior of matter with jaw-dropping accuracy, like a cosmic cheat code. Take the Higgs boson, for instance. Theorized in the 1960s, this elusive particle, the key to explaining why anything has mass at all, wasn't spotted until 2012, when the Large Hadron Collider finally revealed its existence. The moment scientists confirmed its discovery, it wasn't just a win for physics. It was proof that the standard model could foresee the universe's secrets decades in advance. But the model's brilliance doesn't stop there. It's like a master key unlocking three of nature's four fundamental forces: electromagnetism, which lights up our cities and binds atoms together; the strong nuclear force, gluing protons and neutrons in atomic nuclei; and the weak force, driving the radioactive decay that powers stars and even our own sun. Every time you use a smartphone or bask in sunlight, you're witnessing the Standard Model in action. It's so reliable that physicists sometimes joke it's too good, like a clock that never misses a tick, even when we're not entirely sure how it works. Yet for all its triumphs, the Standard Model has glaring blind spots. Gravity, the force that sculpts galaxies and keeps our feet on the ground, is completely absent from its equations. Then there's the enigma of dark matter, that invisible stuff making up 27% of the universe. The model doesn't just fail to explain it, it doesn't even hint at its existence. And let's not forget neutrinos, those ghostly particles that shouldn't have mass according to the original model, yet somehow do. It's as if we've built a flawless map of an island, only to realize most of the planet is still uncharted. So where does this leave us? Some physicists argue the Standard Model is a near-perfect approximation, a stepping stone to something grander. Others whisper it might be a beautiful dead end, like a ladder that gets us halfway up a mountain but no further. The truth is, even its gaps are clues. Every unanswered question why gravity won't fit, what dark matter truly is a signpost pointing toward deeper truths. Maybe the next breakthrough won't come from tweaking the model, but from tearing up the rulebook entirely. After all, history shows us the universe loves to surprise. String theory offers one of the most breathtaking visions in modern physics, a universe where the tiniest building blocks aren't dots but wriggling, vibrating strings, each oscillation composing a different particle. Imagine a cosmic violin with infinite strings, where the note played determines whether you get an electron, a quark, or even a graviton, the hypothetical particle carrying gravity's force. This isn't just poetic imagery, it's a mathematical symphony that could finally unite all of nature's forces under one roof. For decades, physicists have been captivated by string theory's elegance, its ability to weave together relativity and quantum mechanics like threads in a tapestry. But here's where things get wild. For the math to work, string theory demands extra dimensions, not just the 4 we experience, but 6 or 7 more, curled up so tightly we'd never notice them. Picture an ant crawling along a telephone wire. From a distance, the wire looks one-dimensional, but up close, the ant can move around its circumference too. Those hidden dimensions could be everywhere, shaping the universe in ways we're only beginning to fathom. Some versions of the theory even suggest these dimensions aren't static but dynamic, vibrating alongside the strings themselves. Yet for all its mathematical beauty, string theory faces a glaring problem. We have no way to test it yet. The strings are thought to be vanishingly small, perhaps a billionth of a billionth the size of an atomic nucleus. Our most powerful particle colliders, like the Large Hadron Collider, simply can't reach the energies needed to detect them. This has led some critics to argue that string theory isn't science at all but a kind of metaphysics, a dazzling intellectual exercise with no connection to reality. Others counter that groundbreaking ideas often outpace technology, pointing out how Einstein's general relativity waited decades for experimental confirmation. The debate reveals a deeper tension in physics today. Should we chase theories based on their mathematical harmony, even if proof lies beyond our current reach? Or does science demand testable predictions? No matter how elegant the equations, string theorists aren't giving up. Some hunt for indirect clues, like faint signatures of extra dimensions in cosmic microwave background radiation. Others explore the theory's implications for black holes, where quantum mechanics and gravity collide most dramatically. What's undeniable is string theory's ambition. It doesn't just aim to explain particles or forces, it seeks to rewrite our understanding of reality itself. Whether it's the final answer or just a stepping stone, its legacy is already clear. pushing us to think bigger, stranger, and more boldly about the fabric of the cosmos. After all, if history teaches us anything, it's that the universe often defies our expectations, revealing wonders we never thought to imagine. While string theory dreams of tiny vibrating strings, loop quantum gravity takes a radically different path. It suggests that space itself isn't smooth and continuous, but woven from microscopic, indivisible threads. Picture the fabric of reality as a vast cosmic tapestry, where each thread is a loop of gravitational field, knotted together to form what physicists call a spin network. These loops aren't embedded in space, they are space. It's a mind-bending shift. Instead of particles moving through an empty stage, the stage itself is built from these dynamic, interwoven strands. At the heart of this idea is the notion of quantized spacetime, where even dimensions like length and volume come in discrete, tiny packets. Think of pixels on a screen, but for the universe itself. This granularity solves a glaring problem in physics, the infinities that plague classical gravity when it meets the quantum world. In loop quantum gravity, there's no such thing as a singularity, a point of infinite density, because space can't be squeezed smaller than the smallest loop. Black holes, for instance, might not crush matter into oblivion but instead rebound it like a cosmic trampoline. How does this stack up against string theory? Both aim to unify relativity and quantum mechanics, but their philosophies diverge sharply. String theory adds hidden dimensions and exotic objects like brains. Loop quantum gravity strips space-time down to its bare essentials, insisting everything emerges from those humble loops. One seeks harmony through complexity, the other through minimalism. And while string theory struggles with testable predictions, loop quantum gravity offers tantalizing possibilities, like subtle shifts in the speed of light at extreme energies, or echoes of the Big Bang etched into the cosmic microwave background. Yet neither theory has delivered a knockout punch. Critics of loop quantum gravity argue it hasn't yet fully incorporated matter or the other fundamental forces, leaving it incomplete. Meanwhile, its proponents see it as the underdog, a theory born from Einstein's own equations, without the baggage of unobservable dimensions. The rivalry between these frameworks isn't just academic. It's a reminder of how creativity thrives when there's no single path forward. What's fascinating isn't just the science, it's the human drama behind the equations. Loop quantum gravity emerged from the work of physicists like Carlo Rovelli and Lee Smolin, who dared to question whether string theory's dominance was stifling alternatives. Their rebellion wasn't just about math, it was about preserving the spirit of scientific dissent, the idea that breakthroughs often come from the fringes. Whether loop quantum gravity ultimately succeeds or not, its very existence keeps the quest for a theory of everything honest, proving that even in the face of cosmic mysteries, curiosity never runs in just one direction. What if our universe isn't the only one? Imagine a cosmic kaleidoscope where every twist creates a new reality, some with stars and planets like ours, others where gravity is weaker, light moves slower, or even where time runs backward. This isn't just wild speculation, it's the multiverse hypothesis, a concept that's reshaping how physicists think about the theory of everything. If countless universes exist, each with its own unique laws, does that mean there's no single equation to rule them all? Or could there be an even grander framework, a meta-theory that explains why these realities vary in the first place? Take the idea of cosmic inflation, the theory that our universe expanded exponentially in its first moments. Some versions suggest this expansion didn't just happen once, but keeps occurring eternally, spawning bubble universes like froth in an endless ocean. In each bubble, the laws of physics might settle into different configurations, like dice landing on random numbers. This could explain why our universe seems so finely tuned for life. If every possible set of laws exists somewhere, it's no surprise we find ourselves in one where conditions are just right. But here's the twist. If every possible universe exists, does that make the search for a theory of everything meaningless? Or does it simply mean the ultimate theory must be flexible enough to account for infinite variations? String theory adds another layer to the mystery. Some versions propose a landscape of possible solutions, millions of ways the extra dimensions could curl up, each corresponding to a different universe with its own physics. It's like a cosmic vending machine. Press a different button, and out pops a reality where electrons are heavier or the speed of light is slower. But if this is true, the theory of everything might not predict a single set of laws but an entire spectrum of possibilities. That doesn't necessarily negate the quest, it just reframes it. Instead of seeking one equation, we might be hunting for the rules that generate all possible equations, a sort of algorithmic master key. Then there's the quantum multiverse, where every decision branches reality into parallel timelines. In this view, the universe isn't just vast, it's endlessly splitting, with versions of you reading slightly different versions of this sentence right now. While this idea feels ripped from science fiction, it emerges naturally from quantum mechanics math. But if every possible outcome happens somewhere, does that mean the laws of physics are just local bylaws, different in each branch? Or is there a deeper symmetry connecting them? The multiverse forces us to confront humbling questions. If we can't observe other universes, is this even science? Some argue it's more philosophy, while others point to indirect clues like unusual patterns in the cosmic microwave background that might hint at collisions with other bubbles. And if a theory of everything must account for all possible realities, does that make it impossibly broad or unimaginably profound? Perhaps the answer lies in redefining what everything means. Maybe the universe or multiverse isn't just a puzzle to solve but a canvas of endless variation, where the true theory isn't a single note but the symphony itself. Here's the thing about the universe, we've only ever seen 5% of it. The rest is hidden in plain sight, two shadowy enigmas we call dark matter and dark energy. Together, they make up 95% of everything, and yet we can't touch them, see them, or even fully explain them. Think of it like sitting in a dimly lit room, knowing there's an elephant in the corner. You can't see it, but you feel its presence in the way the floor creaks, the air moves. That's how dark matter works. We know it's there because galaxies spin faster than they should, their stars held together by some invisible glue. Without it, the Milky Way would fling itself apart. But what is it? Particles we haven't discovered. A cosmic illusion revealing flaws in our understanding of gravity. Every experiment, from underground detectors waiting for a phantom collision to telescopes mapping the universe's skeleton, brings us closer, or maybe just deeper into the mystery. Then there's dark energy, the universe's most baffling riddle. Imagine blowing up a balloon, only to watch it expand faster and faster with no extra air. That's what's happening to space itself. In the late 1990s, astronomers discovered the cosmos isn't just growing, it's accelerating, pushed by some repulsive force we can't explain. Dark energy is the placeholder name for whatever's doing the pushing, but the label feels almost comically inadequate. Is it the energy of empty space itself, as Einstein's cosmological constant suggested, or something far stranger, tied to undiscovered dimensions or fields? The scariest part, if dark energy strengthens over time, it could eventually tear apart galaxies, stars, even atoms in a big rip. Here's why this matters for the theory of everything. Any framework claiming to explain the universe can't ignore 95% of its content. It's like writing a biography of a person and skipping their heart and brain. Current theories hit a wall when confronted with dark matter and energy. The Standard Model has no place for them. String theory and loop quantum gravity offer hints but no smoking guns. Some physicists wonder if these aren't just missing pieces but clues that we're fundamentally wrong, that gravity behaves differently on cosmic scales, or that our math is missing a hidden variable. The hunt for answers is driving some of the most daring experiments in science. There's the Large Hadron Collider, smashing particles to uncover dark matter candidates like WIMP. There's the Vera Rubin Observatory, scanning the sky for distortions caused by dark matter's gravity. And then there's the Radical Fringe, scientists exploring modified gravity, theories that ditch dark matter entirely, or models where dark energy is a dynamic field, not a constant. Each idea is a gamble, but that's the thrill, the chance that somewhere in the data, the universe might finally whisper its secrets. What's humbling is how little we know. Dark matter and energy remind us that for all our equations and telescopes, the cosmos is still playing its cards close. Maybe the theory of everything won't be a single eureka moment, but a series of revelations, each unraveling a layer of the mystery. Or perhaps the answer lies in something so bizarre, we haven't even thought to ask the right question yet. One thing's certain, until we solve this puzzle, any claim to a complete theory is just a beautiful dream. If the universe could speak, mathematics would be its voice, a precise, elegant language encoding everything from the spin of an electron to the swirl of galaxies. But here's the haunting question. Is this language rich enough to articulate a theory of everything, or are we like poets trying to describe a sunset with a limited vocabulary? The relationship between math and physics has always been symbiotic. Einstein's equations for general relativity, for instance, leaned on the curved geometries of Bernhard Riemann, a mathematician who died decades before his work became the scaffolding of modern cosmology. It's as if the universe had already written the answers, waiting for us to stumble upon the right dialect. Today, the quest for unification hinges on mathematical tools far more abstract: topology, which studies shapes that stretch and twist without tearing, group theory, the algebra of symmetry that underlies particle physics, and Calabi-Yau manifolds, those intricate six-dimensional shapes string theorists believe might hide the universe's extra dimensions. These aren't just fancy jargon, they're the brushes painting reality's portrait. When physicists say electrons have spin, they're not literally twirling, they're borrowing from group theory's playbook, where rotations in abstract spaces describe behaviors no microscope could ever see. Math, in this sense, isn't just a tool. It's a sixth sense revealing patterns invisible to eyes or instruments. Yet for all its power, mathematics has limits, or at least our grasp of it does. Take Gödel's incompleteness theorems, which prove that even in pure math, some truths can't be derived from a set of axioms. Could physics hit the same wall? Some theorists worry we're circling answers just beyond our symbolic reach, like explorers mapping a continent with an outdated compass. Others argue the opposite, that new math waiting to be invented will crack the cosmic code. After all, calculus didn't exist until Newton needed it to describe motion. Maybe the theory of everything demands a revolution in notation, a grammar we haven't yet imagined. The tension between discovery and invention fuels this dance. When Dirac's equations predicted antimatter in 1928, it wasn't by accident. The math insisted on it, even though no one had seen a positron yet. Today, similar hints lurk in unsolved equations. String theory's requirement of 10 dimensions, for example, isn't a bug, it's a feature, a mathematical inevitability. But without experimental proof, it's easy to wonder, are we decoding the universe's blueprint or writing our own? perhaps the most thrilling possibility is that math and physics will converge in a way that reshapes both. Just as quantum mechanics forced us to rethink causality, a true theory of everything might demand new branches of mathematics, ones where infinity is tamed, where dimensions flex and fold in ways that make four-dimensional space-time seem quaint. The irony is delicious. To understand the universe, we might first need to reinvent the very language we're using to describe it, and that's the beauty of this quest. It's not just about finding answers, it's about discovering how much we still have to learn. Gravity is the universe's ultimate rule breaker, while quantum mechanics choreographs the frenzied dance of particles with flawless precision, and relativity maps the graceful curvature of space-time. The two refuse to share the same stage. Imagine trying to blend a ballet with a mosh pit, both magnificent in their own right, but their rules simply don't mesh. This is the heartbreak of quantum gravity, the glaring incompatibility between the very small and the very large, between the probabilistic flicker of particles and the smooth, deterministic pull of planets. Why is this marriage so hard to arrange? Start with the math. In quantum mechanics, forces are carried by particles, photons for electromagnetism, gluons for the strong nuclear force. But gravity, according to Einstein, it's not a force at all. It's the bending of space-time itself. Try to describe that bending using quantum field theory, and the equations explode into infinities. It's like dividing by zero, the framework just collapses. Even worse, gravity is absurdly weak compared to other forces. A tiny magnet can override Earth's entire gravitational pull on a paperclip. This mismatch suggests gravity might play by entirely different rules, or that we're missing a fundamental piece of the puzzle. Enter the Contenders. String theory, with its tiny vibrating strings, offers one path forward by naturally including graviton's hypothetical particles that would carry gravity's force. Loop quantum gravity takes a bolder stance, proposing that space itself is woven from discrete loops, rendering gravity an emergent property of their interactions. Then there's the wild card, emergent gravity, which suggests gravity isn't fundamental at all but arises from deeper, more exotic physics, like the way temperature emerges from the motion of atoms. Each approach has its devotees, but none have delivered a knockout blow. The stakes go beyond theoretical neatness. Without quantum gravity, we can't understand the birth of the universe, where relativity and quantum mechanics must have worked in tandem. Black holes, those cosmic paradoxes where space-time warps beyond recognition, also demand a unified theory. Hawking radiation, the slow evaporation of black holes, hints at a quantum gravitational handshake, but the details remain maddeningly out of reach. And if we ever hope to probe the Planck scale, the unfathomably tiny realm where quantum gravity dominates, we'll need a theory to guide us. But here's the twist. What if the problem isn't just technical but philosophical? Some physicists argue that our very notion of space and time might need reinventing. After all, quantum mechanics shattered classical intuitions about particles. Perhaps gravity will force us to rethink reality's scaffolding. The journey to quantum gravity isn't just about patching equations, it's about discovering whether the universe is ultimately unified, or if some divisions run deeper than we dare imagine. One thing's certain, until we solve this riddle, the theory of everything will remain just out of grasp, teasing us with glimpses of a harmony we can't yet hear. What if everything you see, the stars, the trees, even your own hands, is nothing more than a shadow cast by information written on a distant, two-dimensional surface? This isn't the plot of a sci-fi movie. It's the holographic principle, one of the most mind-bending ideas in modern physics. The concept first emerged from an unlikely place, the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered something astonishing: the entropy, or disorder of a black hole isn't proportional to its volume, as you'd expect, but to its surface area. It's as if all the information swallowed by the black hole was compressed and stored on its event horizon, like a cosmic hard drive. Fast forward to the 1990s, when Leonard Susskind and Gerard T. Hooft took this idea further. They proposed that the entire universe might work the same way, that the three-dimensional reality we experience could be a projection of data encoded on a distant, two-dimensional boundary. Think of it like a hologram where a flat surface creates the illusion of depth when you shine light through it. The holographic principle suggests our universe operates similarly, with the fabric of space-time emerging from a network of information we can't directly perceive. But how could this possibly simplify the search for a theory of everything? For starters, it flips our understanding of reality on its head. Instead of grappling with gravity in 3 dimensions, we might describe it more neatly in 2. String theorists have already found tantalizing hints that this could work. In certain models, calculations that are impossibly complex in 3 dimensions become strikingly elegant when translated to a lower dimensional surface. It's like swapping a tangled knot for a straight line, the same problem, but suddenly solvable. Then there's the AD/CFT correspondence, a concrete example of holography in action. This mathematical duality shows that a universe with certain properties like negative curvature can be perfectly described by a theory living on its boundary with no loss of information. While our universe doesn't have those exact properties, the principle holds a provocative promise. Reality might be simpler than it appears. Skeptics, of course, raise valid questions. If the universe is a hologram, where's the projector? How does information on some distant surface translate into the world we touch and see? And if this is true, why can't we detect the pixelation of space-time, the fuzziness that should come with being a projection? Experiments like the holometer at Fermilab have hunted for such graininess, but so far, the universe looks smooth. Yet the holographic principle refuses to fade. Some researchers argue it could resolve the black hole information paradox, the question of what happens to data swallowed by a singularity. If information is never truly lost, just scrambled on a horizon, it would preserve quantum mechanics' most sacred rule. Others see it as a bridge between gravity and quantum theory, a way to finally unify the cosmic and the microscopic. Whether the holographic principle is the key to the theory of everything or just another stepping stone, it undeniably shifts how we think about reality. It challenges us to consider that the universe might not be built from matter or energy, but from something far more fundamental, information. And if that's true, then the deepest truths of existence might not lie in the stars above us, but in the invisible code from which they're woven. Black holes aren't just cosmic vacuum cleaners, they're the ultimate testing grounds for physics, pushing our theories to their breaking points. Picture a place where gravity is so intense that even light can't escape, where space and time twist into knots, and where the laws of quantum mechanics and relativity collide head-on. It's no wonder physicists see these monstrous objects as Rosetta Stones for decoding the theory of everything. Take Hawking radiation, for instance. In the 1970s, Stephen Hawking made a startling prediction: black holes aren't entirely black. Due to quantum fluctuations near the event horizon, they should slowly leak particles, evaporating over eons. This revelation tied thermodynamics to black holes in a way no one expected, suggesting that even the darkest corners of the universe play by the rules of entropy. But Hawking's discovery also birthed a paradox that still haunts physicists today. If a black hole evaporates, what happens to all the information it swallowed? Quantum mechanics insists information can't be destroyed. It might get scrambled, but it should always be recoverable. Yet general relativity claims that anything crossing the event horizon is lost forever, crushed into a singularity. This clash isn't just academic, it's a crisis for physics itself. Resolving it could force us to rewrite the rules of reality. Some theorists argue that information escapes via Hawking radiation, encoded in subtle correlations between particles. Others propose it's preserved on the event horizon, like a holographic fingerprint. And then there's the radical idea that black holes don't evaporate at all. Instead, they transform into entirely new objects like remnants or even wormholes to other universes. What makes black holes so special isn't just their extremes, it's how they force us to confront the gaps in our understanding. Their event horizons are where relativity's smooth space-time crashes into quantum mechanics' chaotic uncertainty. String theorists see this boundary as a proving ground for their ideas, where extra dimensions or vibrating strings might leave clues. Loop quantum gravity, meanwhile, suggests the horizon could be a mesh of microscopic loops, preventing true singularities. Even the holographic principle got its start here, with the realization that a black hole's entropy depends on its surface area, not its volume. Perhaps the most tantalizing possibility is that black holes aren't anomalies but blueprints. If we can crack their paradoxes, we might uncover universal principles applying everywhere, from the birth of the cosmos to the behavior of subatomic particles. After all, if a theory can explain how information survives a trip into a black hole, it could also reveal how the universe itself preserves its own history. That's the irony. These seemingly destructive monsters might actually be the key to creation, holding secrets about how everything, from the tiniest quark to the largest galaxy, fits together. The closer we look, the more they seem less like dead ends and more like cosmic signposts, pointing us toward a deeper truth. The search for a theory of everything isn't just a battle of ideas, it's a race against the limits of our own technology. Imagine holding a map to buried treasure but lacking a shovel deep enough to dig. That's the frustration physicists face today. Theories like string theory or loop quantum gravity shimmer with mathematical elegance, yet the energy scales required to test them lie far beyond our reach. Take the hypothetical strings at the heart of string theory. If they exist, they'd vibrate at the Planck scale, energies a quadrillion times higher than what the Large Hadron Collider can produce. Building a machine powerful enough to probe that realm would demand a particle accelerator the size of the Milky Way. Suddenly, the line between visionary science and untestable speculation starts to blur. This isn't just about scale, it's about the very nature of evidence. In the early 20th century, Einstein's general relativity made daring predictions: light bending around the sun, time slowing near massive objects that astronomers could verify within years. Today, the stakes are higher and the clues more elusive. Cosmic inflation, for instance, might explain the universe's uniformity, but its telltale gravitational waves are buried in primordial noise. Dark matter particles could be streaming through you right now, yet they interact so weakly with ordinary matter that even the most sensitive detectors might miss them. When experiments span galaxies or tunnel underground for decades without a whisper of proof, skepticism grows. Are we chasing truths or mirages? Some argue this is just how science progresses. Breakthroughs often outpace tools. Consider the Higgs boson. Predicted in the 1960s, it took half a century and a 17-mile collider to confirm. Patience, they say, is woven into discovery. Others counter that without falsifiable predictions, theories risk drifting into philosophy. String theory's landscape of possible solutions, each describing a different universe, raises eyebrows precisely because it seems to explain everything and nothing simultaneously. If a theory accommodates all outcomes, does it actually tell us anything? Yet ingenuity persists. physicists are devising workarounds, like hunting for indirect signatures of extra dimensions in the cosmic microwave background's faint patterns. Quantum computers might one day simulate conditions no collider could replicate, and some anomalies, like the muon's slightly off-kilter magnetic moment, could hint at undiscovered particles tied to deeper theories. Even failures teach us something, narrowing the paths forward, refining the questions. The deeper challenge is knowing when to hold on and when to let go. History brims with beautiful ideas that withered without evidence, from Ptolemy's epicycles to the luminiferous ether. But it also boasts concepts once deemed untestable: black holes, atoms, the Big Bang, that later became cornerstones of science. The theory of everything might demand not just new math or machines, but a redefinition of what proof means. Until then, we're left balancing on a tightrope between imagination and rigor, where the greatest risk isn't being wrong, it's stopping the search too soon. What would it mean to hold the blueprint of reality in your hands? A theory of everything wouldn't just fill textbooks, it would ripple through every corner of human thought, forcing us to confront questions we've dodged for millennia. Start with the oldest puzzle of all. Does the universe have a purpose, or is it just an exquisite accident? If the deepest laws of physics could be written on a napkin, would they whisper of design or simply cold, beautiful inevitability? Philosophers have wrestled with this for centuries, but a unified theory might reframe the debate entirely. Imagine discovering that the constants governing reality, the strength of gravity, the mass of an electron, aren't arbitrary but emerge unavoidably from a single equation. Would that imply a cosmos fine-tuned for life, or just a dice roll in an infinite multiverse where any outcome eventually happens? Then there's the haunting idea that reality might be purely mathematical. From Pythagoras to Planck, thinkers have wondered if numbers are the true fabric of existence. If a theory of everything reduces galaxies and quarks to equations, does that mean the universe is, at its core, a computation? Some physicists argue yes, that particles and forces are just shadows cast by abstract relationships, like characters in a video game rendered from binary code. Others push back, insisting math is merely the language we use to describe phenomena, not the substance itself. But what if the distinction vanishes? What if, as Einstein once mused, the most incomprehensible thing about the universe is that it's comprehensible at all? The implications for human thought are equally profound. For generations, science and philosophy have drifted apart, one obsessed with how things work, the other with why. A unified theory could bridge that gap, forcing us to rethink free will, consciousness, even the nature of time. If every event from the Big Bang to your next thought is dictated by fundamental laws, does choice evaporate? Or could those laws somehow accommodate agency, weaving freedom into the fabric of physics? Theologians might see echoes of a first cause, artists might find new metaphors for creativity, historians would revisit moments when paradigms shattered. Copernicus displacing Earth from the cosmos, Darwin linking life to common ancestry, and wonder if we're on the brink of another rupture. Perhaps the most humbling thought is this: even a perfect theory wouldn't end the mystery. Knowing the rules of chess doesn't make the game predictable. Understanding DNA doesn't capture the thrill of a first kiss. A theory of everything might explain the canvas, but the painting, the messy, vibrant, irreducible experience of being would still demand its own language. And that's the real beauty of the quest. It's not just about solving the universe, but about discovering how much more there is to ask. What if space and time aren't the stage but the performance, an illusion conjured by something far stranger happening behind the curtain? That's the wild promise of emergent spacetime, a theory that turns our cosmic intuition inside out. Instead of treating the universe as a static container where events unfold, Imagine reality as a shimmering mirage, woven from quantum entanglement or the ceaseless flow of information. Picture an ice skater gliding across a rink. From a distance, the motion seems smooth and continuous, but zoom in close enough, and you'll see the ice is actually made of trillions of jostling water molecules. Emergent spacetime suggests our experience of dimensions might work the same way, a seamless illusion built from microscopic chaos. This idea didn't come out of nowhere. It grew from a paradox first spotted in black hole physics. When matter falls into a singularity, general relativity says it's gone forever, but quantum mechanics insists the information it carried must persist. The holographic principle offered a way out. Perhaps the information isn't lost but smeared across the event horizon, like a cosmic fingerprint. From there, physicists began to wonder, if a black hole's interior can be encoded on its surface, why not the entire universe? Suddenly, space-time isn't a given. It's a byproduct emerging from quantum bits interacting in ways we're just beginning to fathom. Take quantum entanglement, that eerie phenomenon where particles instantly influence each other across vast distances, defying classical notions of locality. In emergent spacetime theories, this spooky action at a distance might be the glue holding reality together. Entangled particles could create the very geometry of space, stitching points into a coherent whole. It's like realizing the threads of a tapestry aren't just decorative, they're what give the tapestry its shape. Some models even suggest time itself could arise from the way quantum systems evolve, turning the flow of moments into a cosmic illusion, a side effect of deeper mathematical relationships. Then there's the radical notion that space-time might be a kind of code. In condensed matter physics, exotic materials like topological insulators exhibit behaviors that can't be explained by their individual atoms. Their collective interactions create entirely new properties. Similarly, space-time could be an emergent phenomenon, a pattern that only makes sense when you step back and see the bigger picture. Think of it like a crowd doing the wave in a stadium. No single person is the wave. It only exists because of how everyone moves together. If space-time works this way, then the quest for a theory of everything shifts from finding fundamental building blocks to deciphering the rules of their collective dance. Of course, not everyone's convinced. Critics argue that without experimental proof, emergent spacetime risks becoming a metaphysical fantasy. After all, how do you test whether dimensions are real or just a useful illusion? Supporters counter that the same was once said about atoms invisible until technology caught up. Today, experiments like quantum gravity simulators and precision measurements of cosmic microwave background anomalies might one day reveal cracks in our classical view of space-time. Even if they don't, the mere possibility reshapes how we think about unification. If space and time aren't foundational, then merging quantum mechanics and gravity might not require forcing them into the same framework, but realizing they're two sides of a deeper, stranger coin. The implications are staggering. If emergent spacetime is right, then black holes aren't just objects in the universe. They're windows into how the universe constructs itself. The Big Bang might not be the beginning of time but a phase transition, like steam condensing into water, and the arrow of time. Perhaps it's not an intrinsic feature of reality, but a story we tell about correlations in quantum data. This isn't just tinkering with equations, it's reimagining the canvas on which we thought those equations were written. Whether it's the final answer or just another step toward one, emergent spacetime forces us to confront a humbling truth. The universe might not just be stranger than we imagine, but stranger than we can imagine, at least until the next revolution comes along. Why does the universe seem tailor-made for life? Tweak gravity just a bit weaker and stars wouldn't form. Adjust the strong nuclear force by a hair and atoms would fly apart. Even the vacuum energy, that mysterious dark energy pushing galaxies apart, is bizarrely fine-tuned to a value that allows galaxies, planets, and ultimately us to exist. This eerie precision isn't lost on physicists. It's the heart of the anthropic principle, the idea that the universe's laws appear fine-tuned because, well, we're here to observe them. But is this a profound insight or a clever way to dodge deeper questions? On one side, proponents see the anthropic principle as a necessary lens. If multiple universes exist, each with different physical constants, then it's no surprise we find ourselves in one where conditions allow life. Think of it like winning a cosmic lottery. Of course, you're holding the winning ticket because losers don't get to marvel at their luck. String theory's landscape of possible universes lends weight to this view, suggesting countless realities where forces and particles behave differently. In that context, our universe's fine-tuning isn't mysterious, it's inevitable. Critics, however, call it a surrender. Dressing up coincidence as explanation, they argue, stops us from seeking deeper laws that might determine these constants. It's like finding a perfectly tuned pocket watch in the desert and shrugging, "Well, if it weren't working, I wouldn't be here to hear it tick." Even some multiverse enthusiasts admit the anthropic principle feels unsatisfying, a placeholder until we uncover why the lottery exists at all. Yet the debate isn't just academic, it cuts to the core of what science is. Is the anthropic principle a testable hypothesis or a philosophical shrug? Some point to potential fingerprints of other universes in the cosmic microwave background, or anomalies in particle behavior that hint at broader laws. Others retort that these are speculative stretches, blurring the line between physics and metaphysics. Perhaps the truth lies in the tension itself. The anthropic principle forces us to confront whether the universe is about something or just is. For now, it remains a paradox, both a reminder of how strangely hospitable reality is and a challenge to dig deeper, because even if we're cosmic lottery winners, someone had to print the tickets. What if everything around us, the stars, the laws of physics, even your thoughts, isn't real, but an unimaginably advanced simulation? The simulation hypothesis pushes this sci-fi trope into serious scientific debate, suggesting our universe might be someone else's digital construct. Think of it like the ultimate video game, where we're not players but lines of code in a cosmic program. But here's the twist. If this is true, the theory of everything we're chasing wouldn't describe nature's deepest laws. It would just be the rules the simulators coded into their universe engine. The idea gained traction when philosopher Nick Bostrom laid out a startling argument. If civilizations inevitably create simulations indistinguishable from reality, and if those simulations can spawn their own simulations, the odds say we're more likely to be in one of countless artificial worlds than the original. It's like realizing you're probably not the first person in a never-ending hall of mirrors. Physicists have even proposed ways to test the hypothesis. Some hunt for glitches, tiny inconsistencies in the fabric of reality, like pixelation in the cosmic microwave background or energy constraints that hint at computational limits. Others point to quantum mechanics oddities, where particles exist in multiple states until observed, as potential evidence of processing shortcuts in the simulation's code. But how does this connect to the theory of everything? If we're in a simulation, the ultimate laws might not be elegant equations, but the arbitrary preferences of whoever built the system. Gravity could be set to 9.8 meters per second squared, not because of some profound symmetry, but because the programmers liked the number. Even constants like the speed of light might just be parameters in a cosmic console, tweaked to see what happens. This raises a chilling possibility. The theory of everything might not explain anything beyond the simulation's design document. Not everyone's convinced, of course. Critics argue the hypothesis is unfalsifiable, a fancy way of saying anything's possible without evidence. Others counter that even if we're simulated, the simulator's universe must have its own physics, kicking the can down the road. And then there's the existential itch. If we're just data in a machine, does meaning itself evaporate, or does it deepen, knowing that even simulated lives can ask real questions? The simulation hypothesis forces us to confront the limits of science itself. If reality is code, then decoding it might reveal less about the universe and more about the coder's whims. But here's the irony: whether we're in a simulation or not, the act of searching for answers, testing, questioning, imagining, is what makes us real. After all, even if this is all a grand illusion, the curiosity driving us to peek behind the curtain feels undeniably authentic. Consciousness might be the most intimate mystery we know, the silent observer behind every scientific discovery, the voice reading these words in your head right now. But what if it's more than just a byproduct of brain chemistry? Some physicists and philosophers argue that consciousness isn't merely riding the waves of the universe, it might be shaping them. This idea, radical as it sounds, traces back to quantum mechanics' early days. When Schrödinger's cat exists in a superposition both dead and alive until observed, it begs the question: does consciousness itself collapse the wave function, forcing reality to choose a state? Take the famous double-slit experiment. When particles are fired at a barrier with two openings, they create an interference pattern, as if each particle passes through both slits simultaneously. But the moment scientists place a detector to observe which slit a particle takes, the pattern vanishes. The particles behave like discrete objects. It's as if the universe knows when it's being watched. Some interpretations, like von Neumann-Wigner consciousness theory, suggest the observer's mind is the trigger. Critics, of course, scoff at this notion. They argue that observation in quantum mechanics simply means interaction with any measuring device, not a conscious being. After all, a camera can collapse a wave function just as effectively as a human. Yet the debate doesn't end there. Integrated information theory, developed by neuroscientist Giulio Tononi, proposes that consciousness arises from the complexity of information processing, not just in brains, but potentially in any system with the right architecture. Could the universe itself be such a system? Panpsychism, an ancient idea revived in modern physics, suggests that consciousness is a fundamental property of matter, like mass or charge. In this view, electrons might possess a rudimentary form of experience, not thoughts, but some infinitesimal whisper of subjective feeling. It's a staggering thought. What if the cosmos isn't just aware of itself through us, but is itself a vast, shimmering network of proto-consciousness? The implications for a theory of everything are dizzying. If consciousness is woven into physics, then unifying relativity and quantum mechanics might require accounting for the mind's role in shaping reality. String theorist Bernard Carr argues that mental phenomena could exist in higher dimensions beyond our current mathematical grasp. Others, like Sir Roger Penrose, speculate that quantum processes in brain microtubules bridge the gap between mind and quantum physics, a controversial idea dubbed Or. Skeptics dismiss these notions as wishful thinking, arguing that consciousness studies belong to biology, not fundamental physics. But if history teaches us anything, it's that the universe rarely fits into neat disciplinary boxes. Perhaps the most provocative question isn't whether consciousness belongs in a theory of everything, but what everything truly means. If the cosmos is more than just particles and forces, if it's also experience, meaning, perception, then our equations might need to stretch beyond numbers to encompass the qualitative. It's one thing to describe how a star burns. It's another to explain why its light feels awe-inspiring. The resistance to this idea isn't just scientific, it's almost existential. Accepting consciousness as fundamental would force us to rethink not just physics, but our place in the cosmos. Are we passive observers decoding an indifferent universe, or participants in a reality that somehow includes us as more than accidental guests? For now, the question lingers at the edge of science, too compelling to ignore but too nebulous to resolve. Whether consciousness is a ghost in the machine or the machine itself remains unknown. But the mere possibility reminds us that the universe's greatest mysteries might not lie in distant galaxies or quantum foam, but in the very act of wondering about them. Time feels like the most undeniable part of our existence, always flowing forward, never backward, carrying us from birth to death in one unshakable direction. But here's the cosmic joke: physics doesn't actually care which way time goes. The equations governing particles and forces work just as well whether time runs forward or backward. So why does our reality feel so stubbornly one way? The answer lies in entropy, the universe's slow march toward disorder. Picture a sandcastle on a beach. Left alone, it crumbles, never spontaneously reassembling. That's entropy in action, the reason milk mixes into coffee but never unmixes, the reason you remember yesterday but not tomorrow. This irreversibility is the only thing giving time its arrow, and it's rooted in statistics. When you shuffle a deck of cards, they'll almost always end up disordered, not because order is impossible, but because there are infinitely more ways to be messy than neat. The universe works the same way. After the Big Bang, everything started in an improbably ordered, low entropy state, like a pristine deck fresh out of the box. As the cosmos expanded, that order dissolved into chaos, creating the gradient we experience as time. But here's where things get weird. If entropy dictates time's flow, then at the quantum level, where entropy's grip loosens, does time even mean the same thing? Quantum mechanics treats time as a static backdrop, not a flowing river. In equations like Schrödinger's, time is just a parameter, a label, not a participant. Some theorists argue this means time isn't fundamental at all, but an emergent property like temperature arising from the motion of atoms. Loop quantum gravity takes this further, suggesting time might disappear at the smallest scales, leaving only timeless quantum relationships. It's as if the universe's clockwork melts away when you zoom in close enough, revealing a frozen landscape where before and after lose their meaning. Yet entropy keeps pulling us back to the big picture. Black holes, those entropy powerhouses, might hold the key. When matter falls into a singularity, it doesn't just vanish, it maxes out the entropy budget for that region of space. Some physicists, like Sean Carroll, propose that the Big Bang's low entropy state wasn't a beginning but a transition from a previous high entropy phase, like a cosmic reset button. If true, time's arrow might not be unique to our universe but a recurring theme in an eternal cycle. Others, like Roger Penrose, speculate that in the far future, when entropy exhausts itself, time might literally end not with a bang but a silent heat-death whisper. The real shocker, entropy might not just describe time, it could bridge quantum mechanics and gravity. In black hole thermodynamics, entropy is proportional to the event horizon's area, not its volume, hinting at a deep link between information, gravity, and the fabric of space-time. If a theory of everything can explain why this relationship exists, it might finally reveal why time flows at all. Until then, we're left with a paradox. Time feels like the most real thing in our lives, yet it might be the universe's most elaborate illusion. a side effect of deeper, timeless laws waiting to be uncovered. Supersymmetry burst onto the physics scene like a cosmic revelation, a dazzling idea that promised to tidy up the universe's messy loose ends. Picture a grand ballroom where every known particle arrives with a perfect dance partner. Electrons would twirl with selectrons, quarks with squarks, photons with photinos. This elegant symmetry, affectionately dubbed SUSY, wasn't just poetic, it solved real problems. For starters, it offered a candidate for dark matter, the neutralino, a stable, invisible particle that could be floating through you right now. It also smoothed out the jagged math of the Higgs boson's mass, preventing quantum corrections from inflating it to impossible values. Suddenly, the unruly quantum zoo had order, and physicists dared to hope they'd glimpsed the universe's hidden blueprint. But SUSY real magic was how it bridged the forces of nature. In its framework, the wild divergence between gravity and the other forces wasn't a bug. It was a feature waiting to be unlocked at higher energies. At the scales where supersymmetric particles kicked in, the strengths of all four fundamental forces would converge like train tracks meeting at infinity. It was a vision so beautiful that for decades, SUSY seemed almost inevitable. Nobel laureate Steven Weinberg once mused that it would be too bad if nature didn't take advantage of it. Graduate students flocked to the field, papers piled up, and the physics world held its breath for experimental confirmation. Then came the Large Hadron Collider. If SUSY was real, the LHC's proton collisions should have sprayed supersymmetric particles across detectors like confetti. Yet as the machine ramped up to unprecedented energies, the detectors stayed stubbornly quiet. No squarks, no gluinos, no trace of the neutralino. With each passing year, the parameter space where SUSY could hide shrank, forcing theorists into increasingly baroque contortions to keep the dream alive. Maybe supersymmetric particles were just heavier than expected, but then why did their absence leave the Higgs mass so unnaturally fine-tuned? The elegance of SUSY began to feel like a mirage, its mathematical grace notes ringing hollow without experimental validation. The disappointment wasn't just about missing particles, it was a reckoning for theoretical physics itself. SUSY had been more than a hypothesis, it was a culture, a way of thinking. Entire careers were built on its framework, and its potential collapse left a generation of physicists at a crossroads. Some dug in, arguing that SUSY might still appear at even higher energies or in subtle signatures we're not yet equipped to see. Others began eyeing alternatives, extra dimensions, quantum gravity, even radical rewrites of quantum mechanics. The debate spilled beyond academia, with critics accusing SUSY proponents of moving the goalposts, while defenders pointed out that good ideas often outpace technology. After all, the Higgs boson took 50 years to find. What makes SUSY's story so poignant isn't its failure, it's the reminder that even the most beautiful theories must face the gavel of experiment. Science thrives not on certainty, but on the tension between imagination and evidence. SUSY may yet rise from the ashes, or it may join the ether as one of history's near misses, a cautionary tale about the siren song of elegance. But its legacy is secure. It pushed mathematics to its limits, inspired generations, and taught us that sometimes the universe's greatest lessons come not from the answers we find, but from the questions we're forced to ask when those answers don't arrive. Artificial intelligence is quietly rewriting the rules of physics, not by replacing human genius, but by amplifying it in ways we're only beginning to understand. Picture a supercharged assistant that can sift through millions of particle collisions in seconds, spotting anomalies no human eye would catch, or simulating entire universes with different physical constants to see which ones permit life. This isn't science fiction, it's happening right now in labs from Geneva to Berkeley. Take neural networks trained to analyze data from the Large Hadron Collider. These algorithms don't just process information faster, they detect subtle patterns in the chaos, like finding a whispered conversation in a roaring stadium. When physicists recently used AI to comb through old LHC data, they uncovered rare particle decays that had been hiding in plain sight for years. It's as if we've been handed a cosmic magnifying glass, revealing details we never knew to look for. But AI's role goes beyond data crunching. Some of the most mind-bending theories in physics, string theory's 10-dimensional landscapes, loop quantum gravity spin networks, are drowning in mathematical complexity. Traditional pencil and paper calculations can take lifetimes to navigate these labyrinths. Enter machine learning, which thrives on complexity. Researchers are now training AI to explore the theory space of possible universes, testing which mathematical structures produce stable, life-friendly physics. One team at MIT used neural networks to study Calabi-Yau manifolds, the intricate shapes string theory says could hide extra dimensions. The AI found unexpected symmetries and shortcuts human mathematicians had missed, cutting years off the research timeline. It's like watching a child solve a Rubik's Cube in seconds while adults still struggle with the first layer, humbling but exhilarating. Then there's the tantalizing possibility that AI might invent physics we haven't even imagined. At Stanford, scientists fed a neural network data from quantum experiments without teaching it any underlying theory. Astonishingly, the AI independently reconstructed key equations of quantum mechanics, essentially rediscovering a century of physics from scratch. What if we gave it the unsolved puzzle's dark matter's identity, gravity's quantum origins, and let it propose entirely new frameworks? Some theorists worry this could lead to black box theories, algorithms that predict perfectly but offer no intuitive understanding. Others counter that human intuition has limits. Maybe the universe's deepest truths are too alien for our brains to grasp unaided. The stakes are higher than ever. As particle colliders grow more expensive and cosmic mysteries more elusive, AI offers a way to stretch our intellectual reach. Projects like Google's Quantum AI Lab are already simulating quantum systems no classical computer could handle, potentially unlocking secrets of superconductivity or even space-time itself. But here's the paradox: the same tools accelerating discovery might also force us to rethink what understanding means. If an AI derives a theory of everything, will we recognize it? Or will it feel less like an equation and more like an oracle, whispering answers we can't fully comprehend? The future of physics might not be humans versus machines, but a partnership where each plays to their strengths, our creativity, their brute force brilliance. And in that collaboration, we might just find the universe waiting to surprise us yet again. History has a way of humbling even the brightest minds, and the quest for cosmic unity is littered with elegant theories that crumbled under scrutiny. Take the luminiferous ether, once thought to be the invisible medium through which light waves traveled, like sound through air. 19th century physicists were so convinced of its existence that they built intricate experiments to detect its subtle drag, only to find nothing. Michelson and Morley's famous interferometer, designed to catch the ether's whisper, instead delivered a deafening silence. The universe, it turned out, didn't need an ether at all. Einstein's relativity would later show that light could travel through pure emptiness, leaving this once grand idea to fade into obscurity. Yet without this misstep, would we have ever been pushed to rethink space and time so radically? Then there's the steady-state theory, a mid-20th century challenger to the Big Bang. Touted by brilliant minds like Fred Hoyle, it proposed a universe forever expanding but eternally unchanged, with new matter continuously popping into existence to fill the gaps. It was a poetic vision, cosmic immortality, until the accidental discovery of the cosmic microwave background radiation in 1965. That faint hiss of ancient light, the afterglow of the Big Bang, was the smoking gun that sealed steady-state's fate. What's fascinating isn't just that the theory was wrong, but how fiercely it clung to life. Hoyle, a staunch critic of the Big Bang, a term he coined mockingly, spent years refining his model, searching for loopholes. His stubbornness wasn't mere pride. It was a reminder that even wrong ideas can sharpen the right ones by forcing scientists to defend, test, and refine. Less celebrated but equally telling are the forgotten frameworks, like Einstein's later obsession with unified field theory. Convinced that electromagnetism and gravity must merge, he scribbled equations in isolation, ignoring the burgeoning quantum revolution. His quest, though noble, became a cautionary tale, the danger of falling in love with an idea at the expense of evidence. Meanwhile, Wolfgang Pauli's neutrino, initially proposed as a desperate fix to save energy conservation in particle decays, was met with skepticism. "I've done a terrible thing," Pauli joked. "I've postulated a particle that cannot be detected." Decades later, neutrinos were found, proving that even stopgap solutions can uncover profound truths. These dead ends share a common thread. They weren't failures but stepping stones. The ether's demise led to relativity's rise. Steady state's collapse cemented the Big Bang's reign. Even Einstein's fruitless unification attempts inspired later physicists to think bigger. Science, after all, isn't a straight path to truth, but a winding road paved with trial, error, and occasional brilliance. The irony is delicious theories don't fail because they're poorly reasoned, but because the universe refuses to conform to our expectations. And that's the real lesson. Every wrong turn forces us to ask better questions, ensuring that even our grandest mistakes are never truly wasted. Discovering a theory of everything wouldn't just rewrite textbooks, it would ripple through the very fabric of human culture, shaking our art, our philosophy, even our sense of meaning. Imagine waking up to headlines declaring that scientists had finally unraveled the universe's deepest code. At first, the reaction might mirror the collective awe of the moon landing, an electrifying sense that humanity had touched something greater than itself. Museums would mount exhibits visualizing the equations. Musicians might compose symphonies translating cosmic symmetry into sound. There'd be a surge in students flocking to physics, drawn by the romance of a solved universe. Yet beneath the celebration, quieter tremors would stir. For some, the revelation could feel like the ultimate demystification, reducing the cosmos to a cold equation. Would poets still find wonder in the stars if their secrets felt like solved puzzles? Would philosophers grapple with free will if every thought could, in principle, be traced back to fundamental laws? Technologically, the implications could be staggering. A true theory of everything might not hand us warp drives overnight, but it could unlock paradigms we've barely dreamed of. Understanding gravity's quantum roots might lead to mastery over spacetime itself, not just tweaking it for faster-than-light travel, but perhaps engineering pocket universes or harnessing zero-point energy. Medical science could leap forward if we fully grasped how quantum processes influence biology, potentially curing diseases by rewriting cellular code at the most fundamental level. Yet history warns us that monumental knowledge carries monumental risks. The same insights that could stabilize climate might also birth unfathomable weapons, forcing humanity to confront an old question with new urgency. Are we wise enough to wield the universe's blueprints? Spiritually, the impact could split society like nothing since Darwin. Religious traditions might reinterpret their creation myths as allegories for the newfound equations, finding divinity in mathematical beauty. Others could face crises of faith, feeling the divine had been explained away. The theory might even birth new hybrid worldviews where the Big Bang isn't at odds with a creator, but is simply how the creator's language sounds when spoken into the void. Existential dread could shadow these revelations too. If the theory suggested we're in a deterministic simulation, or that consciousness is merely an emergent property of quantum interactions, would life feel more precious or absurd? Artists and filmmakers would wrestle with these questions for decades, creating works that oscillate between euphoria and nihilism. The most profound shift, though, might be in how we see ourselves. A theory of everything could either crown humanity as the universe's great comprehenders or humble us as fleeting specks in an indifferent machine. But here's the paradox: the very act of seeking such a theory, of insisting the cosmos makes sense, reveals something beautiful about human nature. We're creatures who refuse to accept that the stars are just pretty lights, that existence has no why. Whether the ultimate answer brings comfort or terror, the search itself is a testament to our stubborn, starlit curiosity. And perhaps that's the real cultural legacy, not the theory, but the reminder that we're the universe's way of asking questions about itself. Unlocking the universe's deepest secrets would be humanity's greatest triumph. But what if that knowledge also becomes our greatest threat? The pursuit of a theory of everything isn't just an intellectual exercise. It's a Pandora's box of ethical dilemmas waiting to be opened. Consider the Manhattan Project, where the discovery of nuclear fission, a glimpse into the atom's heart, led to both clean energy and the horror of Hiroshima. Now imagine that scaled to cosmic proportions. Mastering gravity or spacetime could mean clean fusion reactors or catastrophic weapons that warp the fabric of reality itself. The same equations that might one day power interstellar travel could also, in the wrong hands, collapse entire regions of space into artificial singularities. History's lesson is clear: scientific progress doesn't discriminate between saints and tyrants. This isn't just about weaponization, though. A theory of everything could redefine what it means to be human. If consciousness emerges from fundamental physics, as some panpsychists suggest, could we one day engineer or even digitize it? The moral quagmire deepens. Would creating sentient AI based on these principles be an act of genius or hubris? And what if the theory reveals unsettling truths, that we're living in a simulation, or that free will is an illusion? Some philosophers argue that certain knowledge might be existentially dangerous, eroding the very beliefs that give society meaning. The Aztecs, after all, didn't collapse because they lacked astronomy, but because Cortés exploited their cosmological myths. Would a complete understanding of reality unite us or shatter the narratives that hold civilizations together? Yet halting the quest for knowledge carries its own perils. Every major leap in understanding, from Galileo's telescope to CRISPR, was met with fear. The Catholic Church once banned heliocentrism to preserve moral order. Today, we recognize that suppressing truth rarely ends well. There's also the pragmatic argument: if we don't pursue this understanding, someone else will. In a universe where rival civilizations might exist, stagnation could be riskier than progress. The dilemma echoes in modern labs, where researchers studying artificial general intelligence or quantum gravity already grapple with self-imposed safeguards. Perhaps the balance lies in stewardship rather than secrecy. The atomic age gave us the doomsday clock. A theory of everything might demand a new ethical framework, one that weighs discovery against responsibility at a species level. After all, fire warmed our ancestors and burned their villages. The universe's blueprint could be the same, not inherently good or evil, but infinitely potent, waiting for us to prove we're mature enough to hold it. Sometimes the most profound breakthroughs come not from staring deeper into the same microscope, but from glancing sideways at an entirely different discipline. The hunt for a theory of everything has long been the domain of physicists scribbling equations in chalk dust. But what if the missing piece lies in the spiral of a seashell or the flicker of a neural network? Consider biology, where emergent complexity, like the way simple cells self-organize into conscious beings, might hold clues about how fundamental particles give rise to space-time's rich tapestry. Physicist Lee Smolin once speculated that the universe evolves through a form of cosmic natural selection, with black holes birthing new universes like cells dividing. It's a wild idea, but it underscores how biological thinking can reframe cosmological puzzles. Computer science, too, is rewriting the rules of discovery. Machine learning algorithms now sift through string theory's infinite landscape of possible universes, searching for patterns no human could spot. Researchers at Stanford recently trained an AI to generate novel mathematical structures that could describe extra dimensions, essentially outsourcing intuition to silicon brains. And then there's quantum computing, which might one day simulate conditions so extreme they'd vaporize any lab experiment, letting us test theories of quantum gravity in virtual worlds. It's a twist worthy of science fiction. The tools we build to solve the universe may end up reshaping our very notion of reality. Even art plays a surprising role. When sculptor Antony Gormley creates installations exploring the body's relationship to space, or when composer John Cage translates particle collisions into symphonies, they're not just interpreting science, they're expanding how we visualize abstract concepts. String theory's Calabi-Yau manifolds, those intricate six-dimensional shapes, were first sketched by mathematicians but later rendered in stunning detail by digital artists, revealing symmetries equations alone couldn't convey. The Renaissance knew this secret well. Da Vinci didn't distinguish between dissecting cadavers and painting the Mona Lisa. For him, anatomy and aesthetics were two sides of the same coin. Perhaps the lesson is that unification demands more than just new math. It requires new ways of seeing. When chemist Ilya Prigogine won a Nobel for showing how chaos breeds order in chemical systems, he inadvertently gave physicists a language to describe the early universe's turbulence. When ecologists map how information flows through ecosystems, they might be sketching blueprints for how quantum entanglement networks the cosmos. The irony is delicious. To find the theory that explains everything, we may need to stop looking for it in just one place. After all, the universe doesn't carve itself into academic departments. It's a seamless whole, waiting for us to catch up. The future of physics isn't a straight path. It's a sprawling frontier with trails leading in every direction. Some researchers are doubling down on brute force experimentation, like the proposed Future Circular Collider, a 57-mile behemoth that could dwarf the Large Hadron Collider's power. Others are betting on subtlety, designing tabletop experiments to measure gravity's faint quantum whispers. Then there are the dreamers, sketching theories so radical they make string theory look conventional. Ideas like causal dynamical triangulation, where space-time is built from tiny geometric chunks, or entropic gravity, suggesting gravity isn't a fundamental force but an emergent side effect of entropy's relentless climb. The beauty of this moment isn't just the diversity of approaches, it's the recognition that the answer might come from anywhere or require all of them at once. Take quantum computing, for instance. While today's machines are fragile and error-prone, future iterations could simulate quantum gravity in ways classical computers never could. Imagine programming a quantum chip to model the birth of a black hole or the first moments of the Big Bang, watching space-time itself emerge from abstract equations. Or consider astrophysics, where next-generation telescopes like the Vera-Rubin Observatory will map billions of galaxies, hunting for distortions that betray dark matter's touch or cracks in Einstein's relativity. Even neutrinos, those ghostly particles that stream through Earth undetected, could be messengers from beyond the standard model, if we can build detectors sensitive enough to catch their secrets. Yet the biggest breakthroughs might not come from bigger machines, but from quieter revolutions in how we think. The holographic principle and emergent spacetime hint that our very notion of reality could be due for an overhaul. What if dimensions aren't fixed but fluid, flickering in and out of existence like quantum fluctuations? What if the universe isn't a thing but a process, constantly rewriting its own rules? Philosophers of science warn that paradigm shifts often feel like heresy before they feel like revelation. When Copernicus dethroned Earth from the cosmos, or quantum mechanics shattered determinism, the world didn't just gain new answers, it learned to ask new questions. Will we live to see the theory of everything? The optimists point to history's accelerating pace of discovery, from Newton's gravity to quantum theory in just 3 centuries. The skeptics counter that some puzzles, like consciousness or dark energy, might resist reduction to equations, but perhaps the question itself is misplaced. The journey isn't just about the destination, it's about the strange, wondrous detours along the way. Every dead end has unveiled some unexpected truth. Every failed experiment ruled out a universe that might have been. Whether the answer comes in decades or millennia, one thing's certain: the cosmos will keep surprising us, and the best discoveries might be the ones we haven't even thought to look for yet. Public imagination often paints the theory of everything as a magical equation that will decode the universe's every mystery, from why we fall in love to the meaning of existence. But here's the reality: physics doesn't work that way. A unified theory wouldn't explain human emotions, consciousness, or why your cat ignores you. Its scope is profound but specific, reconciling the fundamental forces and particles that govern reality. Think of it like this: knowing the rules of chess doesn't tell you why a player bluffs, just how the pieces move. The confusion stems from pop science headlines that blur the line between metaphysical wonder and mathematical rigor, leaving audiences expecting answers far beyond what physics can deliver. Another persistent myth, that a theory of everything would render all other science obsolete. Nothing could be further from the truth. Even with a complete framework for quantum gravity, biologists would still study ecosystems, chemists would still analyze reactions, and psychologists would still probe the mind. Unification doesn't erase complexity, it grounds it. Imagine finally understanding how a piano's strings vibrate that wouldn't make a Beethoven symphony any less intricate or beautiful. Similarly, knowing how gravity and quantum forces mesh wouldn't diminish the awe of a supernova or the puzzle of dark matter. If anything, it would deepen our questions, revealing new layers of the cosmic onion. Then there's the oversimplification that reduces the quest to a single eureka moment. In truth, unification will likely unfold as a series of breakthroughs, each raising fresh challenges. Einstein's relativity didn't spring fully formed from his head. It built on decades of work by Lorentz, Poincaré, and others. Today's theorists are no different, assembling fragments of insight across conferences, collaborations, and occasional dead ends. The process is messy, iterative, and far from the tidy, final answer narrative sold in documentaries. Perhaps the most misleading trope is the idea that the theory of everything is purely a math problem, divorced from experiment. While equations guide the way, physics lives or dies by data. String theory's critics often highlight this without testable predictions. Even the most elegant math risks becoming a self-referential game. Real progress hinges on experiments like the Laser Interferometer Gravitational Wave Observatory catching ripples in spacetime, or particle colliders hunting for anomalies. The universe isn't a crossword puzzle to be solved on paper. It's a dynamic system demanding dialogue between theory and observation. What gets lost in these misconceptions is the true stakes of the quest. This isn't about crafting a philosophical manifesto or reducing life's richness to cold equations. It's about uncovering the hidden grammar of reality, the rules that let stars burn, atoms bond, and black holes glow. And that's stranger and more thrilling than any myth. The real theory of everything won't answer all our questions, but it might teach us how to ask better ones. Imagine a child staring up at the night sky, not just counting stars but wondering why they shine at all. That's where the next great breakthroughs begin. The quest for a theory of everything isn't just about equations scribbled in ivory towers. It's a relay race across generations, and the baton is curiosity. Right now, in classrooms and backyard telescopes, future physicists are taking their first steps towards solving mysteries we can't yet fathom. But how do we nurture that spark into a flame? It starts with dismantling the myth that science is only for geniuses in lab coats. Einstein struggled in school. Hawking found his voice despite physical limitations. The message should be clear. Groundbreaking ideas don't come from perfect test scores. They come from relentless questioning and the courage to be wrong. Hands-on experiences bridge the gap between abstract theory and tangible wonder. When kids build homemade rockets or simulate black holes with coding projects, they're not just learning, they're living the scientific process. Museums and science centers play a pivotal role here. Picture a teenager manipulating a quantum entanglement exhibit, watching particles teleport in real time, or a young girl chatting with an astronaut via live stream. These moments transform science from a textbook chore into a thrilling adventure. Programs like CERN, Be a Scientist initiative, where students analyze real particle collision data, prove that curiosity thrives when given real stakes. The key is meeting young minds where they are. Gaming platforms can teach relativity through time-bending puzzles. TikTok demystifies quantum mechanics with 60-second thought experiments. Yet inspiration alone isn't enough. Representation fuels ambition. When a black child sees Dr. Hakeem Olusai explaining cosmic rays on TV, or a rural student reads about Andrea Gheze's Nobel-winning work on black holes, they're shown that science belongs to everyone. Historically marginalized groups still face barriers, from underfunded schools to cultural stereotypes. Fixing this demands more than token outreach. It requires systemic change. Scholarships for underrepresented students, mentorship networks connecting them with working scientists, and curricula that highlight diverse contributors like Subramanian Chandrasekhar, who defied racism to revolutionize astrophysics, are essential. The next Einstein might be sitting in an under-resourced classroom right now, doodling equations in the margins of a notebook. The stakes couldn't be higher. Climate change, pandemics, energy crises, these are all problems waiting for minds trained to think across disciplines. A theory of everything won't emerge from siloed expertise, but from thinkers who blend physics with philosophy, art with AI. That's why fostering creativity is just as critical as teaching math. When a student sketches a wormhole during art class or writes a story about time dilation, they're exercising the same imaginative muscles needed to envision extra dimensions. Some of the most profound scientific leaps, like Kerry Mully's inventing PCR while daydreaming on a moonlit drive, came from letting the mind wander. Schools that prioritize standardized testing over exploration risk crushing the very ingenuity they're meant to cultivate. So what's the takeaway? The next generation won't find the theory of everything by memorizing formulas. They'll discover it by asking questions we haven't thought to pose yet. Our job isn't to hand them answers, but to protect their curiosity from a world that often values certainty over wonder. Whether it's a parent pointing out the physics of a rainbow, a teacher turning a cafeteria into a particle accelerator simulation, or a YouTuber animating string theory with playful humor, every effort plants seeds. The universe's greatest mysteries won't be solved by lone geniuses, but by countless curious minds, each adding a piece to the puzzle. And somewhere out there, a child just clicked on a video about black holes, eyes wide with possibility, unaware they might be the one to finally connect the dots. There's something deeply human about staring into the night sky, feeling both insignificantly small and profoundly connected at the same time. The search for a theory of everything isn't just a scientific endeavor, it's a mirror held up to our own curiosity, our stubborn refusal to accept that some doors in the universe must remain locked. Think about the last time you wrestled with a question that had no easy answer: why we dream, what happens after we die, whether we're alone in the cosmos. That itch to know, to understand, is the same impulse that drives physicists to chase equations that might explain the birth of black holes or the nature of time. It's not just about the answers, it's about what the pursuit reveals about us. Consider how often we measure progress by milestones, graduations, promotions, discoveries. But the history of science whispers a different truth. The moments that reshape our understanding often come from the questions we don't solve. Einstein's later years, spent chasing a unified theory he never found, weren't a failure. They were a testament to the value of staying in the dark, of letting the mystery guide you. In a world obsessed with quick fixes and instant gratification, the theory of everything reminds us that some journeys don't have endpoints, they're about the vistas we glimpse along the way. The equations scribbled on blackboards today might not crack the cosmic code, but they'll inspire the next generation to look deeper, to ask better questions. There's a quiet poetry in the fact that our quest for ultimate knowledge is, at its core, a celebration of ignorance. Every time we think we've got the universe figured out, whether it's Newton's clockwork mechanics or the standard model's near-perfect predictions, the cosmos throws us a curveball. Dark matter, quantum entanglement, the accelerating expansion of space, these aren't just puzzles, they're invitations to stay humble, to keep wondering. The night sky doesn't owe us answers, and yet we keep looking up, tracing constellations with our fingers, as if connecting the dots might reveal a message meant just for us. Maybe that's the real gift of this search, not a final equation, but the way it re-enchants the world. When you know that the gravity holding you to the Earth is the same force bending light around distant galaxies, or that the carbon in your bones was forged in the hearts of dying stars, the universe stops being a backdrop and becomes a story you're part of. The theory of everything isn't just a destination. It's the lens that turns every moment into a conversation with the cosmos. And whether we ever find it or not, the act of searching, of daring to ask, is what makes the universe feel like home. As we stand at the edge of cosmic understanding, the theory of everything remains both a beacon and a mirage, always shimmering on the horizon, pulling us forward. Think of how far we've come, from Newton's apple to Einstein's curved space-time, from the chaos of quantum particles to the eerie order of the standard model. Each breakthrough has been like adding a piece to an infinite puzzle, revealing just enough of the picture to keep us hungry for more. Yet for all our progress, the universe still holds its deepest secrets close, teasing us with paradoxes and possibilities. Whether it's the elegant mathematics of string theory or the radical reimagining of emergent spacetime, every path forward is a testament to human ingenuity and humility. What's remarkable isn't just the science, but the sheer audacity of the quest itself. Imagine trying to condense the entire cosmos, the spin of electrons, the dance of galaxies, the very fabric of reality, into a single, unifying framework. It's like trying to capture the ocean in a thimble, yet we keep trying because that's what explorers do. The tools we've built along the way, particle colliders that recreate the Big Bang's fire, telescopes that peer back to the universe's infancy, algorithms that sift through data for hidden patterns, are monuments to our collective curiosity. And even when experiments return empty-handed or theories collapse under scrutiny, we're left not with failure but with better questions. The beauty of this pursuit is that it belongs to everyone. You don't need a lab coat to ponder the universe's mysteries, just a willingness to look up and wonder. Some of history's greatest leaps came from moments of unexpected connection. A mathematician scribbling on a napkin, a grad student spotting an anomaly in midnight data, an artist's sketch inspiring a new way to visualize dimensions. The next breakthrough might come from a classroom, a YouTube comment thread, or a sleepless night under the stars. That's the real magic. The theory of everything isn't just about equations. It's about the human spirit's refusal to stop asking why. So where does that leave us? Not at an ending, but at a crossroads. The journey ahead is uncharted, and that's what makes it thrilling. Maybe the final theory will be scribbled on a blackboard next year, or maybe it'll take centuries. But one thing's certain, every time we think we've hit a wall, the universe surprises us. Dark matter, quantum entanglement, the holographic principle. Each discovery peels back another layer, reminding us how much we still don't know. And that's okay. Science isn't a race to the finish line. It's a conversation with the cosmos, one that never really ends. As you click away from this video, carry that curiosity with you. Talk about it, debate it, dream about it. The greatest theories aren't just found in textbooks, they're sparked by ordinary people daring to ask extraordinary questions. Who knows, the next Einstein might be watching right now, itching to scribble an idea that changes everything. Until then, keep looking up, stay dazzled by the unknown, and remember, the universe isn't just out there, it's in you too. Thanks for joining the adventure. Now go blow some